parts C and D we're going to do together because we're asked to write an expression for the instantaneous rate of change of P at the instant where A equals 2, and then we need to figure out what that is and what it means. So basically we're being asked to calculate P prime of 2 with our limit definition. So limit as h goes to 0 of P of 2 plus h minus P of 2 all over h equals limit as h goes to 0. Now we're going to use our function with 2 plus h as an input. So 25,000 e to the 2 plus h over 5 minus P of 2, which is just our function with an input of 2. 25,000, excuse me, e to the 2 over 5 all over h. Now again, we can't plug in 0 for h right now because that would give us 0 over 0 or an indeterminate form. We could try and simplify this a little bit. H goes to 0. Using properties of exponents, we could rewrite this as 25,000 e to the 2/5 e to the h over 5 minus 25,000 e to the 2/5 all over h. And we could actually take it a step further. Limit as h goes to 0, we can pull out a 25,000 e to the 2/5 on top times e to the h over 5 minus 1 all over h. This is all well and good, but we have no algebraic methods for calculating this limit as of right now. So we're not going to be able to calculate this limit by hand, but we can use our calculator to help us out, because what we're going to do is we're going to enter this and then use smaller and smaller values of h to see what we get. So under our y equals, well, first we turn the calculator on, then under our y equals, I'm going to enter this, and I do need to separate the numerator from the denominator. 25,000 e to the 2/5 can go out front because it's just a constant that's being multiplied by this. Now I'm multiplying by this part here, second e, I got to use x instead of h, divided by 5. So that's my exponent, minus 1. That closed off my numerator. That was that parenthesis right there. Divided by h, which I'm calling x. Now I've already got my table set to allow me to do independent values. So second table, and remember what I want. I want h to get closer and closer to 0. So 0.1, 0.01, 0.001, 0.0001. We could also come in from the other side, negative 0.001. Let's do one of them with a heck of a lot of zeros. So a really small h value. So if we go over here, what we see is it looks like we're converging on something just a little bit above 7459. We'll round that off to the nearest whole number. The reason is because of what we're dealing with. Our numerator was a change in population measured in people. So this is a measurement of people, but it's a rate. Our denominator was a change in time. So the units on this are, again, people per year. So now if we wanted to state a sentence, well, 2 is 2 decades after 2010. So the year that this is happening is 2030. So in the year 2030, the population is increasing by 7,459 people per year. So as opposed to part B, where we had to say on average over 20 years how the population was increasing, we can now say specifically at the year 2030, we expect the population to go up by about 7,459 people. So we could actually make a prediction on what the population is going to go up by between 2030 and 2031. Just another way of thinking about what the instantaneous rate of change gives us.